we have to start. And today it's my pleasure to present our speaker, Yana Kinderknecht, with the talk Physical Origin of Fractional Brownian Motion in Models of Anomalous Diffusion. Please.
Yes, thank you. So I have accepted that the talk is recorded in all my devices. Okay, so thank you for the invitation and for the possibility to give this talk. And today we will discuss physical origin of fractional Brownian motion and models of anomalous diffusion. And first of all, what is it, the anomalous diffusion? So first of all, what is classical diffusion? So classical diffusion, diffusion in physical sense, so we have diffusing particles, and we say that diffusion is classical if the mean square displacement of diffusing particles is proportional to the time increment. So as a mathematical model of this physical process, the classical model is we use Wiener process, and the underlying equation, evolution equation, is the heat equation. And this is the governing equation for Brownian motion in the sense that the solution of the Cauchy problem for the heat equation with the initial data U0 is given in terms of this function, which is like a kind of Feynman-Katz formula where we use our Wiener process. Okay, so in this classical model, we have the following features. So as I said, the mean square displacement of diffusing particles is proportional to time increments. And on the language of processes, this means that the variance of the underlying process is linear in time. Moreover, the underlying process is a Gaussian process, and it is a Markov process. So there is no memory in this system. And of course, this setup can be generalized to Markov processes in general, operator semigroups, and evolution equations related to operator semigroups. Okay, so what is now anomalous diffusion? Again, physically. So physically, it means that we have diffusing particles such that the mean square displacement of them is not proportional to time anymore. That is, the diffusion occurs qualitatively faster or slowly than the classical one. Or it may happen that even the diffusion is as fast as the classical one, but there is no Gaussian process behind this process, behind this phenomenon. Okay, so such anomalous types of diffusion have been observed in many different situations, but in particular there is a quite famous publication of Golding and Cox called Physical Nature of Bacterial Cytoplasm, where they have been considered. The experiment was provided by a single particle tracking method. So they have tracked fluorescently labeled mRNA molecules in living cells of bacteria. And this is the name of the bacteria. And it was reported in this paper that the diffusion which they have observed, tracking this fluorescently labeled mRNA, is a subdiffusion. That is, the mean square displacement of diffusing particle grows like this power law, where alpha is not 1, strictly smaller than 1, approximately 0.74. Okay, so there are several models of anomalous diffusion, and today we are going to discuss 2 of them. So one of them most well-established and investigated, and one of the earliest one is the so-called continuous time random walk model. So what does mean continuous time random walk? It is a random walk, so it's like a path of such a random walk, where a random walker make random jumps. Jumps are given by independent and identically distributed random variables, and these IID random variables may have heavy-tailed distributions. That is, this means that it may happen that big jumps are very possible, very probable, and this contributes to the speeding up the mean square displacement. Increasing the mean square displacements or speeding up the diffusion. And between these jumps, there are waiting times, and waiting times are also random, and they are given by random variables, which are also IID, and they are independent from jumps, and they may have heavy tail, tails, this means that this slows down the diffusion. So if the waiting times are quite long, then the mean square displacement of diffusing particles would vary quite slowly. Okay, so this is a nice model. So the process of the position of the particle is described by this renewal process. And this is a nice process in the physical sense that, this model allows to include sticking and trapping effects of medium via these waiting times. And also big jumps of a random walker allow to incorporate some transport or searching mechanism for speeding up the diffusion. So both subdiffusion and superdiffusion may be obtained via this CTRW model. It is known that the scaling limits of such continuous time random walks are given by processes of this form. So at the time change Markov processes, where this Xi is a Markov process, namely in the setting which I have just explained to you now, this Xi is just a symmetric stable process, which corresponds to a limiting distribution of a sum of heavy-tailed jumps. And this process is time changed by another process. So how it is constructed? So if we have heavy-tailed waiting times, then their sums under proper scaling would converge to some stable subordinator, and then this ANT would converge, roughly speaking, to the inverse, like here. So this is the kind of inverse of this process. So this guy is inverse to a better stable subordinator, and then finally scaling limits of such objects would give us the process of this type. Okay, so time change Markov processes and time change is given by inverse subordinators. And it is known that such type of processes, in particular for stable Xi and inverse stable subordinator as a time change, they have the following governing equation. So you see here we have fractional Laplacian, which is the generator of the Markov process Xi, and we have this Caputo time fractional derivative, which corresponds to this time change, And this equation can be written also in the integral form, where instead of this Caputo time fractional derivative, we have this integral with some kernel, so it's a Riemann-Liouville fractional integral. Okay, so you see, if we consider this type of models of anomalous diffusion, we have such type of underlying processes. They are not Gaussian, of course, and they are not Markov. And such type of evolution equations behind. So we have, again, like a fractional Laplacian, and then generalize, not at the moment, not yet generalized, but just something related to time fractional derivative, this one. Okay. There is also another model of anomalous diffusion, the so-called superstatistical fractional Brownian motion. And this model looks as follows. So as a position of a diffusing particle, the following process is suggested. This process is a so-called randomly scaled Gaussian process, where this is my random scaling. A is the random variable, which is strictly positive. And a Gaussian part of this process is a fractional Brownian motion with Hurst parameter h. And this Gaussian part is independent from the random scaling. So this type of process is a special case of the family of randomly scaled Gaussian processes. And so exactly such type of processes have been considered in different papers as a possible model for anomalous diffusion. And so why actually this process? So just formally speaking, due to this random scaling, this process is not Gaussian anymore. And on the other hand, if we consider fractional Brownian motion, then the variance of this process is no more linear in time. So very roughly, without any physics, just by these two characteristics, one can say, okay, why not to consider this process as a model of anomalous diffusion? But of course, there should be some physical meaning of this process. And that's why, so there is an interpretation. So in the frame of this model, the physical interpretation is as follows. So anomalous diffusion is the result of inhomogeneity on the one hand, inhomogeneity of the ensemble of diffusing particles. On the other hand, inhomogeneity of the environment. That is, when we consider just a classical diffusion, like we have a particle of pollen which lives in water and moves due to kicks of water molecules. All water molecules are the same, so no inhomogeneity. And okay, pollen particle is the only one. But if we consider, for example, some processes which happen in cells, so in living cells, then if we make a single particle tracking, so if we track a particle, then it moves in an environment which is very crowded, and it is crowded by different particles. So the environment is inhomogeneous by definition, by the nature. And also the particles which we track, they are usually complex macromolecules. And even if we want to create identical copies of the experiment, it would not be possible because we are not speaking about photons or electrons, but we are speaking about complex macromolecules. This means that in any case, even if we consider the same art of molecules, the same type, there still will be some different individual characteristics. So the idea is as follows. The fractional Brownian motion is responsible for the nonlinearity of the variance from the technical point of view, and from the physical point of view, it appears due to inhomogeneity of the environment. And this random scaling plays the role of a random diffusion coefficient of a diffusing test particle. And it is random because the inhomogeneity of the test particles. So different particles have different diffusion coefficients. That's why we have this extra randomness. And yes, it is responsible for the non-Gaussianity of the position process. Okay, and why it is written here in red? Because this statement is actually, it was a kind of conjecture. So it was the interpretation, but without any, how to say, any proof or justification, real justification. So actually what I'm going to tell you, what I'm going to present you today is the proof that it is really so, that the fractional Brownian motion can be obtained through the inhomogeneity of the environment. Okay, so this is a conjecture which we have proved in the paper which I'm going to present you today. Okay, so this is the model. So this is the interpretation, and now some examples. So the first example, which was the most studied in the literature, is the so-called generalized gray Brownian motion. So it's a class of processes with these parameters, alpha and beta. So alpha is responsible for the Hurst parameter of fractional Brownian motion, and beta is responsible for the choice of the scaling. So this A beta, so random diffusion coefficient, has Laplace transform given in terms of Mittag-Leffler function with this parameter beta. And it is known that this process has the following governing equation. This means that the solution of this equation with initial data U0 is given in terms of this Feynman-Katz formula, where we have this generalized gray Brownian motion as an ingredient. So if you see here, if we take alpha equal to beta, then we obtain exactly the time fractional heat equation. So roughly speaking, the same equation as we have for scaling limits of continuous time random walks. So it's a kind of extra motivation that this model has relation to physics, because continuous time random walks seems to be a reasonable model, and the governing equations are actually of the same type or even the same. Okay. Another example is the so-called gamma gray Brownian motion. It is again a process of this art, where my random variable A has the following probability density function. So the Laplace transform of this random variable A is related to incomplete gamma function. So this process has been introduced in the papers of Louise Begin with co-authors, and you can find the governing equation for such process in the paper of me and Merton Minarczyk, my co-author and former student. So we plan to submit to archive the preprints. We plan to submit the preprints in the next few days, hopefully. So the equation for gamma gray Brownian motion actually looks is in the same class as for GGBM. So this the equation for generalized gray Brownian motion. So you see here we have a function of time, so t and s, and also a Laplacian. So in more general case, we have here just a pseudo-differential operator whose symbol depends on t, s, and space variable, and actually is a function of the symbol of Laplacian. That is, well, roughly speaking, the equation is of the same art as for GGBM. Okay, other choices of this random scaling also lead to other evolution equations of this art, namely with so-called generalized time fractional derivatives. And in particular, you may find such equations and such processes also in these two papers of me with Christian Bender and my former student Marie Bormann. But I have already given a talk about these results at this seminar, I guess. Okay. Also, there are some publications in the physical literature where such models have been considered as the suitable models. And in these publications, A has been considered with generalized gamma distribution, in particular Weibull distribution, or also with the log normal distribution. So this all just to inform you that a lot of such type of processes have been investigated, at least introduced in the literature, both in mathematical and physical, on their own and as models of anomalous diffusion. And they are related to evolution equations. Their governing equations are evolution equations, which are of the same art as those for scaling limits of continuous time random walks. And of course, these equations, they are non-local in space and time, or at least in time. So you see there is no Markov property. So there is a memory in this physical phenomena. Okay, so coming back to physicality of the presented models of anomalous diffusion, as I said, continuous time random walk is a very reasonable model. At least, yeah, physically, it's clear what is described by what. As I also mentioned, there is this publication of Gold and Cox, where they have investigated by single particle tracking method some fluorescently labeled mRNA molecules in living cells. And they have reported the subdiffusion. But there is also another publication where the authors have suggested a simple statistical test, the so-called p-variation test, to investigate the properties of the paths of the trajectories of the particles. And they have applied their p-variation test to the data of Golding and Cox. And their conclusion is as follows. So the data does not follow continuous time random walks with heavy-tailed waiting times. So heavy-tailed waiting times are needed to make subdiffusion, which is reported here. But seemingly that investigating the paths, continuous time random walk, it is not the proper model. But there is no reason to reject the hypothesis that the data follows fractional Brownian motion. So looking at the properties of paths, so to say, statistically, one would better choose a fractional Brownian motion model. And probably one more remark concerning fractional Brownian motion model. So as I said, yes, about the interpretation. So this random scaling, it is a random diffusion coefficient of a diffusing particle. So this means that if we track only singular test particle, then we don't see this random scaling. So, I mean, the random diffusion coefficient is already realized, roughly speaking, and what we observe is efficiently only fractional Brownian motion. So the main step is to understand the physicality of fractional Brownian motion. And this is exactly what we are going to discuss today. Yeah. Yeah, so what I'm going to present you now is the results of our paper. This is a joint work with Christian Bender, Mirko, and Gianni Pagnini. And so at the moment, archive preprint is available. And what is it about? So as I told you, a conjecture or interpretation of superstatistical fractional Brownian motion model is that fractional Brownian motion is responsible for the appears due to inhomogeneity of the environment. So it was a kind of conjecture, suggestion, and now we are going to prove it. So what is done in this paper? So we consider a dynamical system describing the motion of a single test particle surrounded by n Brownian particles with different masses. So particles with different masses, which gives us inhomogeneity of the medium. Since we have only one test particle, we don't see this random scaling, but this is like a second step, which is almost obvious after fractional Brownian motion is obtained. Okay, so we do it in a fair way. That is, we consider a dynamical system of particles, such that physical principles of conservation of momentum and energy are met. So it's a fair system of particles. And we prove that in the limits. So when the environment is getting to be more and more crowded, in the limit, the test particle diffuses in time according to a quite general non-Markovian Gaussian process, whose covariance function is determined by the distribution of masses of surround particles. So roughly speaking, we have created a recipe how to obtain anomalous diffusion. So how to cook the system of particles. So playing with masses of surround particles and with other parameters of the system, we can cook anomalous diffusion, and actually many different versions of anomalous diffusion. So in particular, with proper choices of the distribution of masses, we obtain fractional Brownian motion as a limiting or as a governing process of the anomalous diffusion, so the limiting process. A mixture of independent fractional Brownian motions with different Hurst parameters, or we can get the classical Wiener process, so classical diffusion, not anomalous one. Moreover, we present some distributions of masses of surround particles, leading to limit processes which perform transition from ballistic to superdiffusion or from ballistic to classical diffusion. That is, we can cook the system of particles in a way that we can observe a changing of the art of diffusion. Yeah. So changing the class of anomality of the diffusion. Okay, so this is what I'm going to present you. So our recipe. So what is the particle? What is the system? So our test particle is a passive tracer with a fixed mass m. A position is described by process x n, and velocity by the process v n, and shows how many particles in the surround we have. So surround consists of n Brownian particles with different masses mkn, positions ykn, and velocities ukn. So this is the system which we have. So positions are given by integration of velocities, and velocities are given here. So you see, so this is the SDE driven by Wiener processes. We have independent Wiener processes for each k. Yes, and we have some drifts. So this alpha is a coupling coefficient. And also we have beta coupling coefficients, and here, so these coefficients explain us how intensively the surround particles kick the test particle. Okay. Sorry. Okay, so in order to have some fair physical properties, namely conservation of momentum and energy, we impose some restrictions, some conditions on parameters. So in particular, the fluctuation and dissipation theorem imposes the following relation. It is given here, where these constants have exact physical meaning. But also for simplicity of the system, we have an extra assumption like this. I'm sorry. In the sequel, we would assume that our masses of our surround particles will be random, independent on Wiener processes. And this means that not only masses are random, but also these coefficients are random because the proportion is equal to constant. And hence, due to this equality, also these coefficients are random. But these coefficients are deterministic. Okay.
Yana,
Yes.
can I ask you, these masses are supposed to be random,
Yes.
but they're not changing with the time. Am I right?
Yes, no changing with the time. No
I
changing with
see.
the time, but
Maybe
changing with n, depending
I see. I see.
amount of.
Maybe this is the one of the reasons why the limiting process is non-Markovian. Yeah.
Sorry, I haven't heard a piece of what you said.
Maybe the fact that they are random, independent from the noises, from Wiener noises, but not changing with the time, is the reason that the limiting process is non-Markovian. Yeah.
Probably. So we have not investigated in this way.
I see. Okay. Thank you.
And also, on the other hand, as a special case, we obtain Wiener process, which is, of course, Markovian. But in general, so you will see the statement of the theorem, and you will see what's going on.
Okay.
And of course, so as I said, we have a recipe how to cook the system. This means that we have to play with all the ingredients to get what we want. And this means that there will be like a series of assumptions, which I will have to clarify. And in particular, of course, the masses will be controlled in the proper way to obtain what we want to obtain.
Okay.
But anyway, masses do not depend on time. That is, we know which particles we should add to the environment, in which proportion, so to say, in order to absorb anomalous diffusion. Well, so this was assumption number one. It was just to make the system simpler. So after this simplification, after adding some assumptions from physics, we obtained finally the following system, which we are going to investigate this system. So pay attention now that for all particles, the diffusion coefficient of surround particles are the same. The constant does not depend on n and k. Okay, this is at the moment that's all changing, roughly speaking, in the system. And now we have a sequence of a series of assumptions. So first assumption is that we control the parameters beta and alpha, so these coupling parameters. So beta has disappeared here, but it was eaten by some physical stuff. Okay, so we have parameters beta and alpha here in the equation of the velocity of the test particle. And we control these parameters by power laws, by power functions, such that A and B are positive. That is, when n tends to infinity, these coupling parameters decay polynomially with these powers. So this is the way how we control these coupling coefficients. Now the most interesting assumption about the masses. So for each fixed n, we assume that our masses are ID random variables with a distribution mu n, and now we want many different things from this distribution. So it is a distribution of masses, that is, it is supported on a positive half line, but actually not on the whole line, but bounded below by a constant, which depends on n. And we control this constant, so the smallest mass, so to say, in the following way, again polynomially, by a power function. And you see d is real number. That is, it may happen that this guy tends to 0. It may happen that this guy tends to infinity, or it may happen that this guy just stays constant. All three cases are possible. Okay, but we control this lower bound for technical reasons. Yeah, we control this lower bound. Moreover, and so what is written here looks awfully, but I have to clarify what is the idea. So mu is a distribution which is supported somewhere here. So it is actually quite natural to compare it with some subordinators, namely with Levy measures of some subordinators. That's why we have this guy, which up to this power in denominator looks like a Laplace exponent of some Levy measure. And Levy measures will appear in very soon, but nevertheless. So we consider this guy without name, just the guy. We also consider a sequence of normalizing constants, and we control this normalizing sequence by, again, power functions. And these normalizing constants should decay because delta is not negative. They decay with n. And we assume that it is possible to choose it in such a way that this guy normalized, when n tends to infinity, this guy converges to something reasonable. So, namely, we have a non-decreasing function, v dot, such that we have this convergence. So this means that it increases. So tends monotonically. And we are interested in this function v. V is the integral of this v dot. We have also some technical assumption. So we control some tails of the distribution mu n, but this is not, so technical assumptions are not important for this talk. And one more assumption on the distribution of the masses, or on the masses themselves, better to say, is that so for each fixed n we have IID, but for different n we have different distributions. But nevertheless, all masses at all or altogether, they are independent. So this family is the family of independent random variables, and of course all masses are independent from Wiener processes. Okay, so this is the main assumption on masses. There is also a technical extra assumption on masses, on the distribution of masses. It is needed only to refine the results about the convergence. It's just a technical assumption. There is no real meaning to clarify. That's why I skipped this assumption. It's just to refine the results. And there is also assumption 5 about the U0. So U0 is the initial data for the velocities of the surround particles. So we have surround particles, and the initial data looks as follows. So they are random variables which are independent from our Wiener processes. And given all the masses, these random variables have Gaussian distribution, which is centered with these variants. Okay. So now all the ingredients are presented. And one more technical assumption that we have a lot of parameters. So we control all the parameters with some power laws. So we have a lot of parameters A, B, D prime, that's it, and delta. So we need some relations between these parameters. And so we have this system of equalities and inequalities, and this system has infinitely many solutions. So solution is not the empty set. So don't worry, it's a nice assumption. You don't need to remember it. It's just some assumption which combines all the parameters. Well, we are ready to formulate a theorem. So fix any T0, and under assumptions 1, 2, 3, 5, 6, so without 4, consider a centered Gaussian process with the following covariance function. So here are the constants which we have. So sigma is here, gamma is here, C alpha and C beta control how these guys behave. C delta is related to masses. So all the constants are given in the assumptions before. And this function V, it is actually up to this constant. It is the variance of this process. And it is, again, is constructed via the distribution of masses, so via mu n. So the statement is that under all our assumptions, the processes xn, which describe the position of the test particle, converge as n tends to infinity to this Gaussian process in finite dimensional distributions. And if we have additional assumption 4, which allows us to get tightness, then we get the convergence in distribution. Okay, so this is the statement. So again, we will come back in a minute how we get this V from the masses. But nevertheless, so what do we see? So playing with different distributions of masses, we can construct different types of anomalous diffusion, also different limiting processes, which are always Gaussian processes of this art. So now not a lot of, but some examples of particular processes and how we create this V starting from mu n, so the distribution of masses of the particles. So example 1, now Levy measures. Suppose that nu is a Levy measure of a pure jump subordinator. So if we have a pure jump subordinator, then its Laplace exponent looks as follows, and it is given by some Bernstein function phi of lambda. So we assume, in this example, we assume that our Levy measure is continuous and does not have second moment. Or better to say, yes, it's not a second moment, we have integral from 1 to infinity. Okay, so this integral is infinity. So we choose d and delta strictly positive and define these sequences in the following way. So we control this lower bound of the support of the distribution mu n by the power law as we wanted. And we have also the upper bound. So my distribution will be compactly distributed. My upper bound can be determined from this identity. So I also control it by power function. And then I define the distribution of the masses in the following way. So it is a measure which is absolutely continuous with respect to the Levy measure nu. And this is the density. So you see, so this measure is supported compactly, but compactly. Then we have this y squared. So this is a very important ingredient, and we have this normalizing sequence of constants. We have chosen this guy in such a way that we are able to construct normalizing coefficients satisfying our assumptions in such a way that mu n turns into a probability measure. So we can choose this guy such that with normalizing coefficients satisfying our assumptions, mu n turns out to be a probability measure. Now, under our assumptions, when n tends to infinity, this guy tends to infinity. This guy tends to 0. So finally, we have a distribution of the whole half line. But nevertheless, so you see the distribution of masses is comparable in this sense with a Levy measure of a subordinator. So in this case, when we consider this normalized guy, it looks like this. And when n tends to infinity, this expression just tends to the integral from 0 to infinity of the same style. And this is nothing else but the Laplace exponent, but at the point gamma t. So this is the formula for Laplace exponent, and this is what we have. In the limit, we have 0 infinity here. Okay, and this is my v dot, and hence this is my v. Okay, so this is the recipe. We start with the Levy measure of a subordinator, and then doing this, properly choosing this, and this, we obtain this variance function of the limiting process. So coming back to the statement of the theorem, the limiting process, the Gaussian process with this covariance. Hence, up to a constant, the variance is Vt. Okay, so this is the recipe. And special cases in this setting, special cases of this example. So if we start with h between 1/2 and 1, my Hurst parameter, if I consider 2h minus 1 stable subordinator, this means that the Levy measure has this form. then using our recipe, the Laplace exponent is like this, and hence the corresponding variance function is like this. So once again, variance is just integral of the Laplace exponent up to a constant. Okay, so this is the variance of the limiting process, hence up to a multiplicative factor, up to a constant. The limiting process is the fractional Brownian motion with Hurst parameter h. And in this example, also assumption 4, which I have not presented, it is satisfied. That is, in this theorem, we have actually convergence in distributions. So I have presented the recipe how to obtain fractional Brownian motion in the limit. Okay, some further examples. Mixture of fractional Brownian motions. So I just start with the Levy measure, which is given by a mixture of stable subordinators, Levy measures of stable subordinators with different stability parameters. And then the Laplace exponent is a mixture of, and then the variance function is a mixture of. And hence you see we have different power laws. Hence the limiting process is actually a sum of independent fractional Brownian motions with different Hurst parameters. And this means that when we observe such anomalous diffusion, the regime changes in time. Namely, for small t's, the smallest power plays the role. So this Vt, so the variance is of this power law for small t. And for large times, the highest power plays the role. That is, when we observe at higher times this anomalous diffusion, the variance would behave like this power law. So the power law which is changing with time. So there is this transition in the degree of anomality of diffusion. Okay, again, in this example, assumption 4 is satisfied. That is, we have a convergence in distribution for the processes. One more example, example 2, the same setting. We have the Levy measure of a pure jump subordinator with Laplace exponent. But now we assume that this guy is finite. But nevertheless, we can do the same recipe. So we consider mu n given by this formula. So it is absolutely continuous with respect to the Levy measure. So this is the density. We again use normalizing constants. And now we don't need to have a compact support. So it can be unbounded from above. But yeah, it is important to be bounded from below in a controllable way. In this case, we may consider our normalizing sequence given by these things, and this would satisfy our assumptions. And again, then the normalized guy will look like this. And when n tends to infinity, this guy would tend to, probably it will stay as it is, or let me check. No, so this is like this. For some d tends to 0, for d strictly positive. Hence, when n tends to infinity, this goes to 0. And hence, in the limit, we obtain just the Laplace exponent again. And from the Laplace exponent, we obtain the variance function of the limiting process. Okay, example in this setting. So again, let nu be the Levy measure of a temperate stable subordinator, where h is the Hurst parameter between 1/2 and 1. So we consider 2h minus 1 stable subordinator. So this is the Levy measure. This condition is satisfied. Then we construct the mu n in accordance with our recipe. Then the corresponding Laplace exponent looks as follows. And hence the variance function of the limiting process looks as follows. And you see a mixture of different powers. So in this case, the character of anomalous diffusion again changes with time. So for small t, you just take Taylor expansion around 0 of this function, and you see that this guy is something like comparable with t squared. So it's a ballistic diffusion. And when t is large, then so this is the law of the variance. So it is just a super diffusion, not the ballistic one. So 2h is smaller than 2. Okay, also in this case, assumption 4 is true. That is, we have the convergence in distribution to this limiting process. Okay, one more example in this setting. We have the following Levy measure for a subordinator. In this case, our Laplace exponent looks as follows, and hence the variance function of the limiting process looks as follows. Again, this means that the observed process of anomalous diffusion changes its character with time, namely for small t's. Again, this function is comparable with t squared. Again, using just Taylor expansion for logarithm, and for large t, this is comparable with t. So it becomes, so we start with a ballistic diffusion, and then with time, the character of diffusion becomes a classical one. Again, in this example, assumption 4 is satisfied, that is, we have convergence in distribution. Example 3, in this example, our masses are just deterministic. So even no randomness, just deterministic masses. So we just add more and more particles in the system with masses, so they are, okay. The distribution mu n can be described by Dirac measures concentrated at such points. Okay, then, so this guy is just my 1 over m star n. So this is a normalization. It looks as follows. And hence, this is my Laplace. Okay, so this is my vt. This is my v dot t. And as you see, so when n tends to infinity, this exponent tends to 0. Hence, this guy tends to the indicator function of the interval where we live. We consider everything in some particular interval from 0 to t0, but actually for any fixed t0. Okay, so this is my vt in the limit. Okay, not this one, but the limit. So this is my vt. And hence this means that the variance is just t. That is, in the limit, we have a Wiener process. and hence we have a classical diffusion. Well, I guess it was enough for examples. So just once again, the statements. So we have a system of particles, and we know how to cook this system, so how to choose the parameters, coupling parameters and masses in a way that when n tends to infinity, so it means that the surrounding particles are more and more crowded. We observe the anomalous diffusion in the sense that the position of the test particle converges in distribution to the process, which is Gaussian and whose covariance has this nice form. Okay, I have some time, perfect. And yes, let me check. Yes, perfect. Now some words about the proof. So there are 3 steps, substantially 3 steps in the proof. And the first step is that under our assumptions on parameters, we may neglect this interaction term, not interaction, but okay, coupling term in this equation. This means that instead of u, which is a solution of this equation, we may consider u tilde, which is a solution of the same equation, but without this term. And conditionally on masses, this is just the Einstein-Uhlenbeck process. So we know this process explicitly. Conditionally on masses. Okay. So we approximate u by u tilde on Einstein-Uhlenbeck processes. We insert it here. And then what we have here, it is just ODE. There is no noise. This is just dv is equal to something dt. So this is the first order ODE with this known guy. So we solve this, and then we find the velocity, and then we integrate it and obtain the position. So, this is the position. So first step, we can kill this term and hence approximate u by Einstein-Uhlenbeck u tilde, and hence we prove that we can approximate the true position of the particle by this process x tilde, which is given explicitly by solving the corresponding equations. Okay, so it was the first step. Second step, we show that when n tends to infinity, this process x tilde can be approximated by the following process. So once again, U tilde is Einstein-Uhlenbeck process conditionally on masses, on all masses. We have integrated and we have a mixture of them. So betas are coefficients which are here. And this guy I have forgotten to explain what is it. This is, oh, I'm sorry. This Rn is just the sum of alphas. Okay, so this mixture is given by these coupling things. Okay, so this is another process. And then step 3, we show that this process tends to the Gaussian process as in the statement of the theorem in the proper sense. So actually the proper sense is a mixing convergence. Mixing, G mixing, where G is a sigma algebra generated by all the masses. It's a mixing convergence and plus needed tightness under assumption 4, and we obtain the statement of the theorem. Okay, one more remark, so please pay attention. So we have like a rescale sum of some nice processes. And so these are the rescaling coefficients, yeah? So once again, we have a sum, and these guys are rescaling, and then nice processes, integrated Einstein-Uhlenbeck process. So pay attention that these scaling coefficients, they are like this, because I recall that the betas Kn were like C beta n minus B, and alpha Kn were like C alpha n minus A and B positive. So this is the sum of alphas. So this fraction has this power, and in assumption 6 we have this thing, and where delta was a parameter which we used for constructing our normalizing sequence m star n. So this is an ingredient for cooking the masses of the particles. So in the case delta is equal to 0, we have seen this case in the example 3, where our masses were deterministic. In this case, this scaling is just the same scaling as in the central limit theorem, classical central limit theorem. But in other examples, we have considered delta, which was strictly positive. In this case, this identity means that my scaling, this power law, so this power is bigger than minus 1/2. This means that the scaling is worse than the scaling in the classical central limit theorem. You see? However, it is compensated by good properties of the Einstein-Uhlenbeck processes. So once again, this guy, this process converges to the Gaussian process, which is presented in the theorem, and it is a scaling sum of integrated Einstein-Uhlenbeck processes. And this scaling sum, so these scaling coefficients are worse than those in classical central limit theorem. So they are like power, but this power is bigger than minus 1/2. But nevertheless, this scale sum converges in distribution to a Gaussian process. Okay, I guess that is all what I wanted to present today. Probably a couple of remarks. That in this recipe, we obtain always either anomalous diffusion, which is super diffusion. So between classical diffusion and ballistic diffusion. So in order to get subdiffusion, which is actually reported, for example, in these living cells, we need to add a potential here in the system. So it is a work in progress. So we hope to get the results soon. And another remark is that, as I said, if we track only one test particle, we don't see this random scaling. But if we assume that, coming back to our assumptions, So if we assume that my single test particle is um, inhomogeneous, we may play here. That is that the coupling coefficient may depend from particle to particle, and hence we may make these constants random. So that is a coupling constant depends on an individual test particle, and hence making this coefficient just a random variable and just inserting, make a slight modifications in all the proof, we obtain the same statement as in the theorem, but the process can, the limiting process is a randomly scaled Gaussian process, not just a Gaussian process, but a randomly scaled Gaussian process. But it is again, so the final version of the text is in preparation. Okay, so thank you very much. Now I think I'm finished.
Thank you for your talk, Yana. And maybe somebody have questions or comments, please. I have several remarks. Firstly, let me point your attention to the book of Peter Kotelenets, Stochastic Ordinary and Stochastic Partial Differential Equations. In this book, he pay a lot of attention, maybe essential percent of the volume to the deriving of motion of interacting particles into the liquid or in other surrounding media, just using physical properties of the interaction with molecular fluids and so on. So it will be, I think, interesting because you can input your assumptions about randomness of this interaction and randomness of masses exactly in his construction. This is the first one. Second one, again, relatively to physics. You mentioned several physical sources for obtaining of such anomalous diffusions. And one such source is adsorption-desorption process when we have a semiconductor which has a relatively high temperature and molecules of the surrounding media are adsorbed and desorbed on this semiconductor, then the resistance of semiconductor depend on the number of absorbed molecules. And there are physical models. The first one is a Langmuir linear model, where the adsorption process is modeled like linear equation with linear differential equation with constant coefficients. But when people consider more high temperature or more different, more various number of molecules is surrounding types of molecules in surrounding media, then they produce nonlinear Langmuir equation, which is exactly like you showed us with this fractional derivative in time equation. Yeah. And they also use Laplace to solve it, to study it, and so on. So it can be a good physical model for your process. And also, since you have the separate noises for every your particle, then it looks like you have some McKean-Russell in the limit, but McKean-Russell equation with some additional randomness inside due to your choices of the mass. So it looks like that you can consider not only scaled Brownian motion or fractional Brownian motion, but you can consider some Makin-Lassov limits with additional randomness inside. Yeah. So already to consider the continuous distribution of the mass. Yeah. It looks like. Also, let me ask you, maybe this is just lack of time, but why you don't say that this process converge not only in the sense of finite dimensional distribution, but in some space of functions like in Skorokhod space or something? Yeah.
All processes have continuous paths. So
okay, but so in C in the space of continuous function, you can guarantee that you have V conversions, yeah?
Yes, yes, but under extra assumption form. So without assumption form, only with the assumptions which you have presented, only convergence in finite dimensional distributions. This example condition 4 is just a technical assumption, extra technical assumptions on this distribution mu n.
But it is natural to look at because in other hand you can at least theoretically face some bad effects like finite dimensional distribution converge, but you have no convergence.
Yes, yes. So this extra assumption 4 is just to get tightness.
Yeah, I see.
That's what I have said. Yes, just to be sure that everything totally fine.
Okay.
But in all examples which I have presented, this assumption is satisfied that we really have convergence in distribution.
This is and the last one is question is just because you get Makin-Lassov limit actually, then why don't you use my equation with interaction? Because if you input some randomness there, then you also will get non-Gaussian on Markovian limit. So let's think about this. Yeah.
Let's think about it. Yeah. Yeah. So it is the beginning of the project.
Okay, good. Okay, maybe some other questions or comments, please. Okay, if there are no other questions, then thank you again for interesting talk. Hope to see you again with the progress in the project. And Georgi, who is the next speaker?
The next and the last speaker in this semester is Gennady Navrotsky.
Okay, very good. So then for today that's all, and see you next week. Bye.
Thank you. Thank you for your coming and listening. Bye.
Thank you. Bye.
Bye. I don't know how to switch off.